Welcome to today's paper reading. Today's paper is titled, Self-Play Preference Optimization for Language Model Alignment. This paper was published on the AR14 preprint by Wu and colleagues from the University of California, Los Angeles and Carnegie Mellon University. The traditional reinforcement learning from human feedback, RLHF, approaches face challenges such as intransitivity and irrationality in human preferences, which parametric models like the Bradley-Terry model fail to adequately capture. To address these issues, the authors propose a self-play-based method called Self-Play Preference Optimization, SPPO. This method frames the problem as a constant-sum two-player game aimed at identifying the Nash equilibrium policy. SPPO approximates this equilibrium through iterative policy updates and has a theoretical convergence guarantee. In experiments, SPPO demonstrated state-of-the-art performance, achieving a length-controlled win rate of 28.53% against GPT-4 Turbo on Alpaca Eval 2.0, outperforming other methods like DPO and IPO. Notably, this strong performance was achieved without additional external supervision from stronger language models. Large language models, such as those developed by Ouyang et al. 2022 and OpenAI et al. 2023, have demonstrated impressive abilities in generating human-like text, answering questions, and coding. However, these models face significant challenges and tasks requiring high reliability, safety, and ethical alignment. To tackle these issues, reinforcement learning from human feedback, RLHF, also known as preference-based reinforcement learning, PBRL, offers a promising solution. RLHF frameworks, as highlighted by Cristiano et al. 2017, and Ouyang et al. 2022, have shown significant success in fine-tuning instruction following LLMs, making them more aligned with human preferences. Most existing RLHF approaches rely on either explicit or implicit reward models. For instance, InstructGPT uses a reference policy ref, established from supervised pre-training, and an explicit reward function trained on human preference feedback data. More recent methods, like direct preference optimization, DPO, use the log likelihood ratio to implicitly represent the reward score. Despite these advancements, parametric preference models like the Bradley-Terry model and the Thurston model do not fully capture the complexity of human behavior, which can be inconsistent and influenced by various factors. In the realm of reinforcement learning from human feedback, RLHF, several methodologies have been proposed. Initially, Cristiano et al. 2017 introduced RLHF, which was later applied by Ouyang et al. 2022 to fine-tune large language models like ChatGPT. More recently, Rafaelov et al. 2024 proposed the direct policy optimization (DPO) method, which is claimed to be more efficient and stable. When it comes to general preference models, Azar et al. 2023 proposed a preference optimization objective based on preference probabilities, while Munoz et al. 2023 formulated RLHF as a two-player game. Yuan et al. 2024 identified the Nash equilibrium policy for multi-step MDPs. Theoretical aspects of RLHF have also been explored, with Zhu et al. 2023 studying pessimistic reward learning and Xiong et al. 2023 proposing a reverse KL regularized bandit. Swami et al. 2024 introduced self-play preference optimization, SPPO, focusing on multi-round MDPs. In the context of preference learning, a text sequence X is given, and two responses Y and Y are generated. An autoregressive language model Pi can generate responses following a specific probability decomposition. A preference oracle provides feedback on which response is preferred. The Bradley-Terry model is used to learn a reward function, which can be estimated by maximizing log likelihood. This leads to an optimization problem that can be solved using policy optimization algorithms. In cases where human preferences are non-transitive, a general preference approach is used, identifying the von Neumann winner as the Nash equilibrium in a two-player constant-sum game. The self-play preference optimization, SPPO, algorithm is grounded in a theoretical framework that iteratively updates the policy to converge to the optimal policy. This framework relies on a multiplicative weight update mechanism, where the updated policy in each round is derived from the previous policy. The optimization objective of SPPO is approximated using L2 distance and can be effectively approximated with finite samples, ensuring a convergence guarantee. The SPPO algorithm itself involves generating synthetic responses, annotating these responses with preference data, and then optimizing the policy based on this annotated data. The experiments utilize the Mistral 7B Instruct v0.2 model and ultrafeedback dataset, which includes around 60,000 prompts. The dataset is split into 3 portions to prevent overfitting during fine-tuning. The ParaRM model, based on DeBerta v3, is employed as the preference model, trained on high-quality human preference datasets. Experimental results show that the SPPO method consistently outperforms other baselines, with significant improvements in length-controlled win rates across multiple iterations. Table 1 presents the evaluation results of various models on Alpaca Eval 2.0, focusing on both normal and length-controlled win rates. The Mistral 7B SPPO ITER3 model stands out with the highest length-controlled win rate of 28.53% and a normal win rate of 31.02%. The table highlights that SPPO consistently improves performance across iterations, outperforming other baseline models that tend to generate longer responses. Additionally, the use of the ParaRM reward model for re-ranking at test time consistently enhances performance across all models, including SPPO, which achieves high win rates without strong external supervision like GPT-4. The results also include fine-tuning outcomes for Llama 3-8B Instruct, showing steady performance improvements. Table 2 presents the Alpaca Eval 2.0 leaderboard results, showcasing the performance of various models in terms of normal and length-controlled win rates. The Mistral 7B SPPO model demonstrates its capability to outperform not only larger models, but also proprietary models like GPT-4. Specifically, the Mistral 7B SPPO, best of 16, variant achieves competitive results against GPT-4 0613 and Llama 370B Instruct. Additionally, the Llama 3-8B SPPO model exhibits even superior performance, highlighting the effectiveness of the SPPO approach in enhancing model alignment and performance. Figure 1 illustrates the win rates of the SPPO model against GPT-4 Turbo, both with and without length control, on the Alpaca Eval 2.0 benchmark. The figure demonstrates that SPPO consistently improves its win rates over iterations, indicating effective optimization. The inclusion of length control highlights the model's ability to perform well even when output length is regulated, which is crucial for avoiding the reward hacking phenomenon. This performance is significant as Alpaca Eval 2.0 is a robust evaluation tool with a high correlation to human assessments, providing reliable insights into model capabilities. Table 3 presents the evaluation results of SPPO fine-tuning on the Open LLM leaderboard. The data shows that SPPO significantly enhances the base model's performance across various tasks, achieving a new state-of-the-art average score of 66.75 for Mistral 7B and 70.29 for Llama 3-8B. However, it also reveals a notable decline in performance in subsequent iterations of DPO, IPO, and SPPO. This suggests that while alignment with human preferences can boost performance in some cases, it may not always be beneficial and could potentially harm overall model performance. Figure 2 presents the MT-Bench evaluation results for the SPPO models. On the left, it shows that Mistral 7B SPPO ITER3 outperforms all baseline models with an average score of 7.59. Despite initial performance drops in the first 2 iterations, the final iteration of SPPO shows improvement over the base model. The right side of the figure displays a radar chart of MT-Bench results for Mistral 7B SPPO, highlighting significant gains in roleplay, reasoning, math, and coding tasks. Figure 3 illustrates the pairwise win rates among the base model, Mistral 7B Instruct v0.2, DPO models, IPO models, and SPPO models, evaluated using ParaRM 0.4b as a judge. This judge may favor models that produce longer outputs. The figure highlights that SPPO iteration 3 consistently outperforms SPPO iteration 2. Additionally, Both SPPO and IPO models consistently outperformed DPO across all iterations. However, in the final iteration, IPO surpasses SPPO in performance. Despite this, SPPO remains superior on standard benchmarks evaluated by more powerful judges like GPT-4, such as Alpaca Eval 2.0 and MTBench, as well as on the Open LLM leaderboard. Figure 4 presents the evaluation results of Alpaca Eval 2.0 on self-play preference optimization, SPPO, models with different mini-batch sizes, specifically k equals 2 and k equals 5. The evaluation focuses on both normal and length-controlled, LC, win rates, expressed as percentages. The figure illustrates that while k equals 5 initially shows better performance in the first iteration, this advantage decreases in subsequent iterations. Additionally, it highlights that k equals 2 demonstrates a reduced tendency to increase output length, providing insights into the robustness of SPPO models to variations in mini-batch size. The paper introduces self-play preference optimization, SPPO, which significantly improves upon existing methods like DPO and IPO across multiple benchmarks, including Alpaca Eval 2.0, MTBench, and the Open LLM leaderboard. SPPO integrates a preference model and uses a batched estimation process to align LLMs more closely with human preferences, avoiding issues like length bias reward hacking. However, there are theoretical limitations, such as the reliance on assumptions about model expressiveness and input space coverage. Additionally, the current experiments are limited by computational resources, suggesting the need for broader validation with more models, datasets, and benchmarks. Future work could focus on addressing these limitations and further optimizing the approach. Table 4 presents generation examples from our fine-tuned model using SPPO across different iterations. The prompt involves determining the relationship between two participants in a dialogue, using specific relationship codes, 0 for spousal, 1 for sibling, and 2 for child/parent. In the scenario, Speaker 5 inquires about the relationship with Dr. Richard Burke, who is identified as the father of Dr. Timothy Burke, the on-call doctor. The model's responses evolve across iterations, refining the understanding and application of the relationship codes. Table 5 illustrates the evolution of the character Roman Brady in the NBC soap opera Days of Our Lives through different iterations of actor portrayals. Initially, Wayne Northrop played the role from 1981 to 1984, followed by Drake Hodgson from 1986 to 1991. Northrop returned to the role from 1991 to 1994, and since 1997, Josh Taylor has been portraying Roman Brady. Each actor brought their unique interpretation to the character, contributing to the show's long-running storylines. Thank you for watching.